Hello, Professor Elliott. A brief overview of the BJT common emitter amplifier. The common emitter amplifier has a large voltage gain, and it's a good and because it's a BJT, has very linear, low distortion operation. Depending on the needs of the application, it always depends on the needs of the application, will determine which amplifier type and technology, whether it's a BJT, JFET, or more likely a MOSFET amplifier. But they all have their places. The amplifier. So we're talking about bringing in a sine wave. Okay. We've got a function generator here, so this is sine wave only, and this is a very poorly drawn sine wave. Comes in to point V in. It's our input voltage. Our output voltage V out is going to get a sine wave that looks like that. If those of you who are paying close attention, you will notice that the phase between those two waveforms is not the same, and that's true. The common emitter amplifier has a 180-degree phase shift between the input and output, which you can see very nicely on the 2-channel oscilloscope. Okay, so let's just identify the main bits. I have other videos with the detailed calculations, but capacitor C1 is called the input coupling capacitor. Its function is to pass the AC input at Vn into the base of the BJT, but it will not allow the base bias voltage to backfeed into the AC source. Okay, so it keeps the AC over here, and it's AC and DC here, but it blocks the DC. C2 is called the output coupling capacitor, and that'd be that one there. It does the same function, but at the output side. It blocks the DC voltage on the collector from passing through to the output. So we have pure AC coming in from the function generator, and we have pure AC exiting the amplifier at V out. The capacitor is just keeping the DC bias voltage in its place. C3, that's called the emitter bypass, sometimes called the bypass capacitor. Look at my other videos. I have the AC model. Its function is to hold the emitter at AC ground. Okay, so the microfarad, the size of the capacitors, these are all electrolytics typically, by the way. As you know, the reactance of the capacitor decreases with increases in frequency. So the microfarad value is established to, or selected, to make the reactance essentially zero over the frequency range of the amplifier. And if we do the full AC model, we simply replace each one of these with a dead short circuit, which means then if the reactance of C3 is 0, that means this resistor, the emitter resistor, is shorted to ground, which makes the emitter terminal at AC ground. Okay. If you remove that capacitor, the emitter resistor RE will be visible to the AC, and the voltage gain will decrease dramatically. That's in another video. But Okay, using the voltage divider formula, solve for the voltage from at the base, so it's the base to the ground. Okay, 0.7 volts between the base and the emitter is the emitter voltage. Take the emitter voltage divided by the emitter resistance is the current. You already know from my other videos that the collector and emitter currents are 99.9% the same. VRC is the voltage across the collector resistor, so just take the current IC multiplied by RC. And then the collector to emitter voltage is simply the difference between, take this voltage here, subtracted from that, and that's just the balance. Okay, so this voltage here floats up and down to always, as the current fluctuates slightly, due to beta variations, VC goes up and down. But that's where that is. The amplifier, again, I have other videos that describes how to calculate it using the actual component values. That's beyond the scope of today. In broad terms, treating the amplifier like a black box, the amplifier voltage gain is simply the output voltage divided by the input voltage. Okay. DC low line. DC low line, we plot voltage collector to emitter, collector saturation current, this current IC sat, at that point we assume that the transistor is fully turned on. And if the transistor is fully turned on, then the collector to emitter voltage is equal to 0. So in that case, then, if this was 0, then we could calculate the current, the theoretical current through the BJT using that formula there. I have that detailed in other videos. The collector to emitter voltage VCE off is, if the collector current is 0, what's the collector to emitter voltage? It's like equal to VCC. So these are sort of the upper and lower ends of the sandbox, if you will. This is the actual collector current and the actual collector to emitter voltage, and this is the Q, or Q stands for quiescent point, which is the operating point. I think that's the last page. All right. Thank you very kindly. Have a great day.